Dr. Andrew Brenner is a Senior Program Director for Quantum Spatial based in Ann Arbor, Michigan, and has worked in geospatial data analysis for over 25 years. Andrew heads up the hydrology and natural resource programs for Quantum Spatial and focuses on using imagery, LiDAR, and other sensors to create data sets that can be integrated into GIS decision-making processes. Andrew has a PhD in environmental physics from Edinburgh University, UK, and a BSc in agriculture from the University of Reading, also in the UK. I'll let you take it from there.
Okay, and can everybody see the video?
Yes.
Perfect, thank you. Well, so I'm going to do a short video and then be open for questions. So, good afternoon. My name is Andrew Brenner. I'm a Senior Program Director for NV5 Geospatial, powered by Quantum Spatial. Many of you will know us as Quantum Spatial, and we've been working in the area collecting LiDAR for Wisconsin for the last few years. Kurt Contrusi is also at this conference, attending the conference, and feel free to visit him at our virtual booth. I also want to talk about our technical team. Kathy Power is technical specialist. She has developed most of the work I'll be talking about, working with Misha, the domain expert. First of all, I just want to talk a little about who we are. Many of you know us as Quantum Spatial. We are now NV5 Geospatial. Still the same people, still doing the same stuff. And we have many assets for acquisition, both fixed wing, rotary planes. We have an enhanced UAS group as part of becoming NV5. And we also do a lot of work in topobathymetry and hyperspectral and thermal imagery. So don't forget those if they meet your needs. We will then take those data and then convert it into spatial data. And that's really what I'm going to be focusing on, not the acquisition, but really the spatial data analysis. And then we build enterprise GIS systems that manage those data. What we do, we tend to break it into three parts: acquire, analyze, and answer. We acquire data, we analyze it to create sort of GIS data sets you're all familiar with, and we use that to answer questions within a geospatial enterprise system. What am I going to talk about today? So really what I want to do is focus in on hydrography, talk a little bit about the history of hydrography, understand how LiDAR plays in that, talk about how we can develop stream networks and watershed boundaries using LiDAR, the advantage of standardization, and sort of wrap it up with a summary. So the first thing I'm going to do is talk. So to understand where we are now, it's important to look back in history and understand where we came from. Initially, topographic maps were created from fieldwork. Then they got created using imagery, and many of us may remember the initial release of the digital 1 to 100 NHD digital line graphs in 2000. That was sort of the move into the digital arena. Then it was necessary to get the more detailed information, the 1 to 24K information, into the digital arena, and that started giving us much more detail. The 1 to 100K then got attributed to the NHD plus, and then the USGS moved to blend the NHD plus with the high resolution 1 to 24,000 to create what we call NHD high res plus. The data now exists across the whole of the US, or pretty much the whole of the US, for this NHD plus high resolution that has the high resolution data and the attribution associated with it. A lot of energy has gone into creating a standardized data set that applies for multiple applications. The standardized data set, as we'll see later, is sort of critical. Then along comes LiDAR. LiDAR is an incredible technology that allows us to understand the elevation of the ground, and the elevation of the ground drives where the water flows. This starts to cause a little bit of chaos. As soon as we have LiDAR, we want to start mapping hydrology. As we understand from the second law of thermodynamics, if we don't expend energy, everything moves to chaos. So a lot of energy has been dedicated to standardizing NHD, WBD to date. USGS has done a fantastic job doing that, and we've all benefited from it. As LiDAR comes into the domain that we're playing in, everyone wants to start creating their own hydrology. And so what we have is the standard NHD, which is nice and organized, but if we don't pay attention to it, we're going to everybody's going to start generating their own NHD and WBD, and we start to see that fragmented. And so this is not something that has a desirable result. So we have to start thinking about how do we develop hydrology so we don't have that fragmentation that will cause us a lot of pain in the future. An example of this sort of thing, this is from an unnamed state. If we have multiple data sets saying the same thing, then we have multiple views of reality. There is a lot of energy we've all expended in the past trying to bring together disparate data sets. And so with the advent of LiDAR, it is now much easier to develop all these data sets so that they are consistent. And so what we want to do is build a program that benefits from a unified process. Doesn't mean that it can't be adapted to different applications, but we want something where all the geometry is the same and we're not arguing about lengths of rivers, etc. So that sort of gives you a little overview of my thinking about how we want to approach hydrology from LiDAR. Now what I want to do is talk about the technical approaches that can be taken, and these are sort of the approaches that USGS is proposing. So what I want to talk about is a term called Elevation Derived Hydrology. This can be derived from LiDAR. It can also be derived from IFSAR or any other elevation measurement. And really, it brings together the hydrology or hydrography with the elevation. Make sure that we're not going up sides, water's not flowing on the sides of mountains. It also brings the NHD attributes to a higher resolution. We can either do it at the 1 to 24,000 scale, or we can go to a much higher resolution looking at smaller tributaries. The movement into the digital sphere allows us to use a lot of mechanistic computational methods, and it allows us to derive the data set using these methods. However, we have all found that these methods in themselves don't provide all the answers we want, and we still need expertise and quality control. So we started off with USGS funding 5 watersheds to look at different landscapes to create both an improved delineation at the 1 to 24,000 scale, but also to derive higher resolution at what we're calling the local scale, and then attributing those data sets using information from the NHD, bringing that together, bringing it into the NHD database. So the source data is QL2 data. That's data that exists in Wisconsin. There we have, they use the LAS files. We have hydro-flattened DEMs. This is all stuff that comes standard out of the USGS 3 dep. We also have some break lines, and then we have the current NHD data and the NAPE imagery for looking at. These 5 watersheds were spread across the US in different landscapes. Just sort of run through these areas now so you can see some are agricultural, some are coastal, some are in the foothills, and some are in the marshlands. So there's two approaches we used. One is using what probably people are familiar with the arc hydro routines, and this is what we call the flow accumulation approach. In this one, we take the bare earth DEM, we look at the flow, we calculate flow direction, we calculate flow accumulation, which is the number of cells that flow into a particular cell. And once that flow exceeds a certain threshold, we expect surface water to start running. Now, there are many issues with not necessarily issues, but there are many considerations with the bare earth DEM comes out of LiDAR. LiDAR obviously can't see below the ground, and so we have to enforce that in order to ensure flow through culverts, under bridges, etc. And so we look at where the water pools, we determine whether that is a real pool or whether it's an artificial pool, and we enforce the flow underneath roads, underneath bridges, and through any false barriers. The second approach is one where we start to look at not just the flow accumulation, but we also look at the landscape. We use an approach called Geomorphons. Geomorphons allows us to look at river valleys. It allows us to look at river valleys in multiple scales, so large landforms, under small river valleys, tributaries, down to erosion channels. And we have to determine when we want to call a valley an actual stream. So we have these two methods. We then have to determine when's a stream. So this sort of shows you a little bit of what happens when we set a different flow accumulation threshold. We can see that, in this landscape, we have a large number of water bodies. We have a large number of small tributaries. Those aren't all real. What we have to do is understand where these are true flow lines, and so we need to look at where there's actually a channel, and that's where the geomorphon, looking at profiles, starts to come in, and we need to come up with rules that dictate when is a stream and when is it simply a flow accumulation that doesn't have any meaning. So we go through this process of delineation, through flow accumulation, through geomorphons, and then we create a flow network that we're happy with. We then bring in the information that we have from the existing NHD, so the larger streams will have information, but there also will be new streams, new tributaries that doesn't have information, that will have some we'll put some default information on. There'll also be things like artificial flow connections that allow us to connect rivers through water bodies into the output, and we'll talk a little bit about that later. So this gives you some idea of how the resolution change as we move from the 1 to 24,000 to the higher detailed areas. This is a 1 to 24,000. We can see where those streams are. We can see where the water bodies are. This is when we start moving to that local scale. We can see that we're bringing in much more detailed tributary information that can then be used to help understand the flow. We also have to bring into the workflow a degree of manual editing and QC. We have to make sure that all the streams stay in their channel. We also have to manually correct where streams deviate. Sometimes the area is too flat for the algorithm to accurately delineate the flow. We may need to put in artificial connectors in order to go underneath the ground. And we also need to remove the false positives where there is no evidence of channelization in the ground model. What we're doing is we're creating a line from a raster, and so on the left-hand side, we can see that if we don't do any smoothing, we get a very graded approach. We see a very jagged approach, which is what you tend to see from a raster to vector conversion. If we use the standard arc smoothing, we can smooth it, looks nice. However, the river can move outside the channel, which is something we want to avoid. And so we've developed a smoothing routine that both smooths the data set and maintains the river in the channel, which is one of the requirements for USGS approval. If we look on the right hand side, if once we put that river in that center line, we can see that if we actually use the Z values directly from the LiDAR, we can see that the downstream, the water will not necessarily go downstream, it will go up and down. This is just because of the variation in the LiDAR relative to where we're putting the line. That obviously causes problems in terms of downriver flow. And so what we have to do is smooth that in order to ensure that water is constantly flowing downhill in our models. Again, another example of that. So stream delineation is only part of the overall effort. We also have to delineate water bodies, and as we know, water body boundaries change from place to place, and they change from time to time. The LiDAR does derive water bodies, but only those greater than 2 acres. When we look at the requirements for EDH and the NHD, the requirement for water body delineation is much smaller. And so it is necessary to delineate water bodies that are much smaller than are delineated in the LiDAR. One of the ways we do this is using object-based image analysis, OBIA. We use imagery, we use the LiDAR information, we use terrain descriptors, and we create a set of segments. Those segments utilize the intensity, the slope, and allow us to consistently delineate the water land edge in an automated fashion. So given the examples on the right hand side, we can see that they are quite complex water channels that we're able to delineate accurately using this type of analysis. And we found that this is both consistent and reproducible over large areas. Once we've delineated that water body, we then have to create an artificial path. What we have is water flowing into the water body and out from the water body, and it's necessary for us to route that. Obviously, this is not real, it's a cartographic abstraction, but it allows us to model water flow through that water body out the other side. And we've developed algorithms that allow us to track the water flow through these systems and out the other side and label those with the NHD requirements. Once we've brought together all this information, we then bring the attribution, as I mentioned before, wherever we can, we'll bring attribution from the existing NHD. We will also bring in information from local knowledge where possible and from visual inspection. Many of the streams that we're delineating through this method do not have information associated with it, and so are often provided with a generic stream attribution. Once we've got all this information, we bring everything together. We bring together the streams, we bring together the artificial flows, we bring together the connectors, and that allows us to create the new EDH dataset that is compliant with USGS standards. It will fit into your modeling system, and it will allow you to flow from the top of your watershed through all the obstructions down out to the bottom of the watershed. That information is provided in an NHD compliant layer that's ready for conflation we then run it through the conflation tools from USGS, and then that can be ingested into the national databases. What we expect to see at the end of this process is greater detail, greater accuracy, and greater currency. So we're going to see on the left-hand side the 1 to 24,000 delineation that's accurate. That is then complemented by that local scale level of detail. And on the right-hand side, we can sort of see where the current NHD was, and then the new EDH at 1 to 24,001 and at the local scale. So another thing that we have done is integrate the underground flow in the sewer system with the overground flow based on the LiDAR. This project was done in Washington, D.C., where we modeled the overland flow using the methods that we just discussed and integrated that with the underground flow based on the storm sewer system. This allows us to understand how the storm sewer system will operate under high rainfall conditions. This particular case was for a combined sewer overflow modeling exercise. It also allows us to create very small, in this case, HUC 16 sewer sheds that allows us to understand how a best management practice or how a pollutant leak will flow within the system. This can be something that could be applied in Wisconsin. So it gives you a flavor of what we have been doing using the EDH, some of the methods that we've embarked on, developed, expanded on. It is very easy for someone to take a LiDAR data set and run an ArcHydro process on it and say, here's my hydrography for my watershed. The next few slides, I want to talk about the advantages of applying a standardization, adhering to a standard for any development in Wisconsin. You're sort of at the beginning of the process, and this is where it is worth discussing internally where you want to go. When we started this process, the EDH standards had not yet been developed, so we helped develop those, understand the pros and cons and what things need to be considered. EDH specifications by USGS are now available. I'd encourage anybody who's interested in this to review those, understand them, and provide comments back to USGS about it. As you know, USGS is very receptive to any thoughts from the public on their standards, but definitely something worth considering. What's the value for Wisconsin to adhere to these standards? So the first one is maintenance and distribution. USGS is the steward of NHD and WBD. The state stewards are the ones from the state perspective who maintain it. It reduces your cost for maintenance and distribution if you can leverage off the system developed by USGS, and there's a huge amount of thought and effort has gone into developing that. The other thing, which is probably as important, is the standardization for the application. What we can see on the right-hand side of the slide is that in this case, the NHD plus, but in the future, it will be EDH, will provide that information that can be linked through all the custom applications that are developed to work off that database that will help us with understanding wetlands, fish, dam behavior, levees, water quality, the storette data, the reach files. These are all things that we work with in the water arena on a regular basis, having that standardized addressing system, having that standardized guaranteed quality control format allows us to have confidence in how we are going to apply the information to decision making. The other key thing is that Wisconsin doesn't exist in isolation. It also has water flowing into it from other states. And so having consistency between what exists in Wisconsin and what exists in the other states allows you to model water flow across state lines. The other also important thing is that USGS takes great pride in its data and therefore applies the quality control tools across all data sets coming into its databases, and that will reduce some of the burden of Wisconsin to do that themselves. What are the implications? Well, it's going to cost more in the short term. Adhering to standards, as we know, requires jumping through more hoops than we would normally like to jump through. But in the long term, it really will save you money because you'll only have to do it once. The value you're going to get from the data is going to be much greater, and you're going to be able to ask much more complex questions with fewer resources. We're not going to have to say, how do I bring these data sets together to answer my question? So to wrap up, LiDAR's changing the way hydrography is created. It makes sense to use a standardized workflow and produce data that fits into the NHD and WBD formats. This is a decision that people in Wisconsin will have to adhere to or decide whether they don't want to adhere to it, but I would encourage going in that direction. This way we all work with the same data standard as an individual. I hate being restricted by standards, but as a scientist, I love working with standards. It reduces the costs of doing the work and it enhances our ability to come to conclusion. As LiDAR rolls out across the whole of the state of Wisconsin, everybody's going to be generating hydrography from these data sets. And so coming up with a plan on how the state steward, how the individuals want to manage those data is pretty important and timely. Because if without those discussions, you'll find that everybody will be creating their own hydrography, and once they've created their own hydrography, there will be very little interest for them to change it to a state standard. We have plenty of time for questions. Feel free to reach out to myself or my colleague Kirk with any further follow-up questions, and I will be around for the discussions during the conference. Thank you.
Great, thank you, Andrew, very much appreciated. So we do have plenty of time for questions at this point. I've not observed any questions come into the chat. If anybody wants to unmute themselves, or maybe even better, raise your hand, we could call on you that way, or if you'd like to type a question in the chat, we could do it that way. So we do have a few minutes for any questions. Don't be shy. You answered all questions, apparently, Andrew.
Well, I think I posed more questions than I answered, so I'd be very interested in getting people's thoughts.
Well, we'll give people a minute to think about this.
Yeah. Hey, Andrew, this is Jim Giuliano.
Hey, Jim.
How you doing?
Good.
So how do we estimate costs?
So it is actually, because we've been working with USGS for the last 2 to 3 years, we have been developing a cost profile. So USGS are working up sort of a cost model. We've also worked up a cost model, and really it depends on the number of features, obviously area, and then the number of features. So if you've got very few streams, then there's much less work. If you've got a lot of wetlands and small tributaries, it's more work. Flatter agricultural areas are more difficult than mountainous areas. So we do have a cost model. If you said, estimate me the cost of doing Wisconsin, we could definitely do that. If you wanted to talk to USGS and say, give us an estimate. You can't pin me down to a number on the phone on the meeting right now, but definitely it's,
come on.
We understand enough about doing it now to be able to work up costs. I think one of the things that is really important is to understand, to get local buy-in, and so making sure that the data that's produced can get reviewed by locals, and there is that cost to for the local buy-in. But yeah, it is an estimatable.
Okay.
And we've got
so in Wisconsin, we like to do things weirdly. We like to do things locally, and so we're going to have to develop a program that benefits from that sort of scheme. But as you know, watersheds don't conform to nice political boundaries. So we're gonna have to probably do it in not whole state kind of chunks, but maybe Huck 10s or Huck 12s, in down to that scale to get it started.
So USGS recommends that we do Huck 10s.
Okay.
We have done Huck 12s, and you can take you could take a county boundary and say how many Huck 12s go into that county. That can be done. It's more procedural for checking out and editing some of the NHD. You have to do it on a Huck 10 basis. So that's sort of where I would start, and then sort of either work up or work down from that. But definitely you could do it.
So where does the water bodies like the lakes and the shoreline and what kind of source that doesn't directly come from the LiDAR? You need something else.
Well, so I'm going to separate those two things. So the lakes, we will generally map the lakes based on the LiDAR or imagery. As you know, lake boundaries will change dependent on the weather conditions. I'm not sure how dynamic they are in Wisconsin. They're definitely down in the southeast. They're pretty dramatic. Sorry, southwest. So we do map down to, I think, about a 1/4 acre with the EDH. What gets mapped at the from the standard LiDAR is 2 acre units. So we are mapping much smaller water bodies. And that's one thing. Now the coastline is something different, and it's a little different because there's a whole lot of legal things wrapped up with the coastline. So we're doing a project for USGS which involves coastline down in Texas, and so there is currently discussion about which coastline to use, whether to use the standard NOAA coastline or to extract it from the data. And I think that generally we will take the approved coastline and not adjust it because of all the legal ramifications. But there are some discussions around that. But water bodies, inland water bodies, are much easier to update.
So we've got a few other questions coming in. We'd like to give a chance for some other folks to jump in here. So Howard from Madison wants to know, is your stream vector smoothing algorithm proprietary?
Our stream vector algorithm right now is proprietary. It is, we developed the IP, so yes, it is in public domain. Okay, great. Jennifer Borlick, I'm not sure if this question is still in context, but I'm going to ask it anyway. She asks, how does this fit in with FEMA flood plains? I think she just Yeah.
wondering in general, perhaps.
So it actually is a great question. And, one of the things, there's the floodplains and there's the wetlands. So historically, FEMA would use a different data source to NHD, that would use a different data source to NWI. What we're seeing now is that the LiDAR is becoming the standard data source for all three of these data sets. And so what we're looking at is, how does the work that we expend on EDH apply to both FEMA and to NWI? And so I think that it is really valuable for us to look at that in the context of those three programs, because the work that you do in terms of hydro enforcement of the DEM, which is a significant amount of work, is applicable to that FEMA floodplain question. Now, what we do with EDH doesn't do exactly the same as the FEMA analysis, but the source data that we create can be used for that FEMA floodplain analysis. So it is part of the discussion. It's not identical. And I think bringing these three data sets together is definitely the way of the future. But I wouldn't say that everybody is on the same page on how that happens.
Great, thank you. Another question here came in, and I don't know, Andrew, if you can answer this or not, but 15,000 lakes in Wisconsin, is anyone working on LiDAR bathymetry for them?
Well, it's probably a better question for Jim. We do fly bathymetric LiDAR, and we have flown it. We've flown it definitely in the Great Lakes area. I don't know how much we've flown in Wisconsin. So mapping of the inland lakes, I think, is something that is really valuable. Bathymetric LiDAR is more expensive than topographic LiDAR. And it is really good when the water is clear. It's not very good when the water is very muddy. So I know some of these inland lakes have quite muddy water columns, and it wouldn't work great there. But definitely the Great Lakes area and some of the clearer lakes, that the bathymetric LiDAR system would be very effective for it. But as to whether it's happening, I don't know.
Fair enough. Last question that we need to wrap up here, and this is USGS providing funding or cost shares for the EDH program?
Well, it depends who you talk to. What I would say is USGS sees EDH in the same way as they see the LiDAR 3DET program. So they see this as being something that they want to be involved in. They're looking for partnerships. It really, the ability for USGS to fund it really depends on the amount of money they get in their budget and how that's allocated. So what I would say is that the desire is there, but until the funding is available, that the magnitude of that is unclear, and definitely probably something to follow up with USGS on that.
Great, thank you, Andrew. So on behalf of WLA, thanks very much for your time and energy today. We very much appreciate it.
A pleasure. Thank you for the opportunity, and certainly feel free if anybody's got any questions. I'm happy to answer them.
Excellent.